Live. We are recording. Wonderful. Welcome everyone. Thank you for joining us at the Kitchener-Waterloo Video Tech Meetup. It's April 28th, 2026. Today we have Luc Trudeau, and I'll let Luc introduce himself. Go ahead, Luc.
Sure.
Thanks.
Thank you very much. So I think it's my second time here at Kitchener-Waterloo Talks. I'm really happy to be here and share my afternoon with everybody. I'm happy to see the turnout. So we're going to talk about overfitted codec and the idea of, what if the decoder was the image? And this is an image of Kitchener-Waterloo. That's what we're talking about before the recording. Yeah, okay, it's changing. There you go. So you might know me from LinkedIn. I do these posts. I've posted a few times about overfitted codecs. It's something that I've started to get interested in probably last summer, kind of playing a lot with Python demos, made my own implementations, decided to attend the Click 2025 competition, which has been this kind of learning-based image compression competition that's been going on for many years now. And I wanted to be there, kind of talk with everybody and see the competition, see the results. And the idea behind this talk is really just to kind of share my journey, what I've learned, what I think are interesting, and what's coming up. So think of this talk as more like Overfitted Codecs 101. So we're not going to do any of that complicated stuff. So if you're here for the complex math or the advanced knowledge, you're probably going to be a bit let down. This is going to be a bit more about like insight. How does it work? Get a feel for it. Very visual, a lot of images. And what we're going to talk about is this idea of overfitting, which is usually kind of this negative term. And we're going to put it in a positive way, whereas that this time around, we want to overfit because we're going to overfit to a specific image. So instead of thinking of this encoder that can encode every image or any image, think of like a specific encoder that was designed to encode only a single image, right? And so it's more like it's memorizing the image more than it's actually learning to encode. So that's going to be the idea here. Obviously, the other class of solutions are called autoencoders, and these are like generic encoders that can encode anything that are also based on machine learning techniques. So we're not going to talk about those today, but it's also a very interesting field. But for me, I think what really my passion is about is a lot more on the overfitted side, because it's this kind of new, unique idea that only like machine learning can give us. So and don't worry about it. Like I said, there's nothing complicated here. So I'm just going to go back and do some fundamentals. So we're going to see a few things just to make sure everybody understands everything. So I just wanted to show you that there's two types of bits. So there's the bit, which is the unit of storage. If you have a hard drive or whatever, there's so many bits on it. So it's kind of like a place where you can store things. But when I talk about a bit, it's more in the Shannon type of a way. So it's more like information theory. So a bit is an amount of information. So it tells you how surprising something is or how unsurprising it is. So two examples I give you from this image is if you have the blue sky, right? Blue sky is very easy to predict, very easy. There's a lot of it. It comes up a lot in the image. So there's low surprise there, or low information, or there's less bits there. But if you think of the building, if you look at the building, then that building doesn't come up a lot in the whole image. It's got texture, it's got pixels that have all these different values. So in that one, if I'm trying to predict it, it's going to be a lot harder to predict. That's going to be high surprise. It's going to have more information or more Shannons. Right. So this is something we're going to keep in mind here for this talk. So when we're talking information versus information bits and not just storage bits. The other piece, that's the fundamental piece, can't get away from it, is the multi-layer perceptron, or your neural network. So just to make sure that everybody gets that, I'm pretty sure everybody knows it by now, but you've got basically these hidden layers which are filled with neurons, and the neurons are all interconnected to one another. And the connection between neurons are called weights. And basically the data comes in through the weights, and you have an activation function, and this function will trigger, and that will go further down into the network until you reach your final solution. And the idea there is that you've got just this huge amount of very simple functions, but you can do these very complicated things. And I think I don't need to give any examples. Everybody knows all the crazy things we can do now with machine learning. So just the idea here, we're going to be talking about those. So just so we get the naming out of the way and everybody's on the same page here. So for the activation function, it's going to come up. So I'm just going to present it. We're going to talk about mostly ReLU. So ReLU is a rectified linear unit. So as you can see, there's the first part where, I don't know if you can see my cursor or not, but let's try this here. There we go. This part here, which is all 0, and then it activates and it triggers past a certain point, and then there's like a saturation. So basically, this is the simple function, and you just put a lot of those together, and you can do like a bunch of crazy things. So we want to use this to learn images, to memorize images, and to compress images. So the idea that really kind of got me curious, or that really kind of inspired me or made me wanted to dig into this more, was this idea that with MLPs, you could actually get rid of the pixel grid, right? So instead of having your sensor data and storing that in a matrix of pixels, you could actually store that in a function, right? This machine, like this multi-layer perceptron, which would act as a function, and it would give you the image out. And the idea there is that now you become independent to resolution. The input can be sensor data. The input can be a lot of different things. And the output can be, you could zoom in to images since there's no more resolution. There's like all these implications that are interesting. But then to me, what always seemed the problem was the fact that, this network's a lot bigger than just a grid of pixels, right? You may have like millions of parameters. So in terms of like information theory, it just felt like, how could you store this in so much information and get something competitive? So that's what always kind of set it back. But we're going to see these kind of contributions that have been made to the field that allow it to reach very competitive levels to, what we're used to in image compression right now. So one of the first kind of big moments that happened for me was when I started digging into implicit neural representations. These are used for many things, not just like image representation, but they are used for 3D scenes and things like that. And what was interesting here was, or what was counterintuitive to me, was the fact that the input to the network is like X and Y. Ooh, that's not great. Anyway, so the input to the network is X and Y. So you're basically giving the coordinates that you want, so which pixel I want, and then the network tells you what color that pixel is, which is, to me, it felt really counterintuitive. Like, how can this even work? But it turns out that it works quite well. And what you do is you take your image, you'll just sample random points from this image, and basically feed that into the neural network. So on the first pass, like all your weights are random. So it's going to give you just a terrible prediction, and you're going to compute the error based on what the pixel value was. And then by backpropagation, what's going to happen is that the algorithm will start optimizing the weights so that the color it gives you actually matches the color at that position, and it will start to actually learn the image that we're seeing. So the weights will get updated. You send another pixel in, you run it through the network, and then you keep going. And if you do this, not hundreds, but really like thousands, think like 10,000, 50,000 times, you start to actually see the image get imprinted inside of the neural network, which is interesting. We can actually see it here. So here is basically the x-axis here is the number of training steps you're going to do. And after that, you can see snapshots, and this is the error curve. So basically, when you usually do machine learning, you have two curves. So the first curve is for your training error, and the other one is your kind of validation error to avoid overfitting. But in this case, we actually want overfitting. So we only check one curve, and we don't really mind. So we really want this network to over-optimize and to learn exactly this image. This is not a small network. So it's got two inputs, so X and Y coordinates. The first hidden layer is 256 neurons. The other is 256 also. And then at the end, it comes out with one, grayscale value. So basically, if you add in all the biases, you end up with 132,609 parameters, and you're encoding this very small image, right? So I think for a lot of people, this is very counterintuitive because you're like, well, just a few pixels and you're throwing all this, heavy machinery to compute it. But put that aside for now. Let's just keep looking at this and seeing how it works. So we're seeing that these are kind of the initial weights, and then the image will start to kind of form itself, and slowly you can see the cameraman kind of appear here as we go. So one of the limitations here from this approach is that it's the ReLU is a bit too simple for something like images. So think of a ReLU as kind of drawing a line, right? And what we actually want is more something like a wave. So basically, Sirens was proposed as this idea to do implicit neural representation, but with sinusoidal periodic signals. And anybody with a background in image compression knows that we use DSTs, so discrete sine transforms or discrete cosine transforms. So the idea of having like a sine periodic signal makes a lot of sense. So to me, that was also like, oh, this is a no-brainer. This, we know this will work. And it actually improves the network quite a lot. So before with ReLU, it was hard to see because the image was small, but the image would be a bit blurry and you wouldn't get 100% of the details. Whereas now with the Sirens approach, the learning is a lot better. I don't know if you're able to see this over the call or not, but what's interesting is it almost looks like waves that are forming inside the image, and then it forms the final image a lot quickly. So a lot quickly we get the shape of the image, and then we can get final details. So with Sirens, you can actually get like perfect reconstruction after some time. But again, this is like a very big network. It's a lot of parameters for just this small, simple image. So things need to improve a lot more before we can actually do something useful with this. And also the other issue is that this is actually targeted at image representation, but what we would like is probably image compression. So the first kind of work in this field on image compression was called COIN. And basically, it's the idea that you can compress an image using an implicit neural representation. So it basically just picks off where a siren left off and just makes a codec out of it. What it does is actually just, so the bit streams are the weights and the biases of the network. As we saw, there's a lot of those. And then the idea where compression comes in is that instead of having like a quality flag, what it does is it just has a table, and when you want a certain level of quality, it'll use a certain size of the network, right? So the bigger the network, the more the heavier the bit stream will be, and basically the more fidelity you'll get out of it. So that's kind of the idea behind that idea. And the gradient descent will try to optimize the mean squared error. And you can download that. You can play around. It works. What it does for quantization is just that it quantizes to 16-bit floats, and then that just gets shipped out, and that's your bit stream. So here's an example of it running. You can see the image. Again, we'll just sample a bunch of different values. We feed that into the network. Once we're happy with our network, we just serialize it and then send it to bitstream. And then on the decoder side, when you're ready, you just take your bitstream. It's going to be all your weights. So you're able to reconstruct your multi-layer perceptron. And then what you need to do is very simply just query every pixel that you want. So in this case, you could query all of them. If you wanted to, you could query them all in parallel. There's no dependencies between the pixels. And you get the full reconstructed image out. So this is kind of the first proof of concept, if you want, that the idea works, that you could do it. There's a lot of problems if you come from like a modern compression background. You're going to be like, there's lots of things that don't work well here. So we're going to look at them and see, how the field improves. So over the years to fix these different issues. So the big problem is the absence of rate control. So rate control in this case is kind of done as what's called a meta parameter. It's done outside of the network. It's basically, you decide your quality up front, like I said, and it'll determine the size of the network. So that's not ideal, because we know that encoding is usually content based. So what you want to do is kind of adjust to your content. And what we come to know as the gold standard in compression is usually this function here, which would be along the lines of distortion plus a weighing factor, usually called the Lagrange, and then the rate, right? So what does it cost me to do this decision in how many bits versus the distortion I get from doing this distortion, and then I can optimize my choices based on that. So we would want this inside of our neural network or our approach. So there's a big problem with that. Whoops. There we go. There's a big problem with that. And the problem is that for a neural network to be able to do this gradient descent, so for it to be able to optimize the weights, the function for the optimization, or the function for the error, has to be differentiable. So you need to be able to take the derivative of that function. MSE works great. We know that, but the problem with rate is that you can't do it. Because it's not the problem that the network doesn't know its own size. It's more the fact that when you do entropy coding is a discrete operation that's not differentiable. It basically says, here's a symbol. This symbol will cost you, I don't know, 5 or 10 bits to encode. Well, that value 5, you can't differentiate. So this is kind of a big problem with this approach. But actually, it was solved for autoencoders before. So there was already kind of a solution to this approach. And that's something also that really interested me in this field, is the fact that we're taking these concepts that have been known for a long time, like entropy, and we're discovering these new ways of doing it that are like continuous or differentiable. And we're kind of reinventing or rediscovering these ideas, but like in a different way. So the idea here, basically, you would have a symbol, and then you'd say, well, this symbol is that many bits, right? And then, like I said, you can't take the derivative of that. So what we're doing for soft entropy is we're saying, well, for this same symbol, I'm going to give you this function instead, right? And this function, I can take the derivative of it. And then, so that can actually be used for gradient descent. Now, the problem is obviously that you're going to bleed into the other symbols. So the other symbols get a small bump. So you can actually tailor that to the problem space you're doing, but at the same time, it gives you the ability to, if you do this operation many, many times, these small errors will factor out, and the big contribution will win compared to the other ones. Now, this is super interesting because now we have a neural network that not only can adjust to the error inside the image, but it can adjust to its own size, right? So it knows how many Shannons it's going to produce, it knows how much information is in it, and it can optimize this information in terms of how much distortion it will produce inside the image. So that might sound very complicated, but it's actually a very cool thing, and that's what we're going to look into. And then the other piece that usually we'll have in modern compression that we didn't see in Coin is this concept of context, right? So any format that you want, or that that you like, will have some form of prediction or some way to exploit things like spatial correlation. So PNG will allow you to predict a pixel from different pixels that were neighboring to it. JPEG 2000 will use these wavelet compositions. So it's probably hard to see here, but this is like the rendition of the original image, very small, and then you've got all the deltas for different subbands of wavelets, right? And then you can rebuild your image from there. And then any video codec you want, H.265, AV1, H.264, whatever, they'll use some sort of extrapolation for pixels. So it'll take like these reconstructed pixels that they already have, and then you'll use it to build your prediction. And from there, you're only going to encode the residual, right? So this would also be something we'd want that would be interesting to see in coin or in a coin successor. And the other thing is somehow you'd want the neural network to be able to optimize that as well. And they actually did come up with the solution. So this is a simplified version of a tool called Coolsheik. We'll see it a bit after, but this is the idea here. So basically, instead of giving it the XY coordinates for the image, now what you do is you have this thing here called the latent, right here. And your latent is just this multi-resolution representation of your image. It starts out with random values, just like the weights of your network. And then as you go through the steps, because this one is also differentiable, you can backpropagate. And so basically what happens is so let's say I wanted to do this pixel here, right? I think I've highlighted it. I get its corresponding values in the latent. So I'm going to upscale this latent here so that it matches the resolution of my image. Same thing here. And then I'll have 3 input values for my neural network, and then I'll run the whole network. It will give me this nice RGB triplet. And then same as before, what I'm going to do is look at the ground truth and basically compute the error. And then this error now has the MSE, which we talked about before, the mean squared error. It also has our weighing term, and it also has now the rate. And now the rate is actually the size of the whole network here and also the size of the latent. So this goes into our backpropagation because all of this is differentiable. It'll update the weights, but it also updates the latent. So this starts to take form. The latent starts to take form and starts looking more like the image. And then the weights start looking at some sort of enhancement network or something that can make it better. So basically, it's like if this thing was creating like a pure Shannon or a pure information here version of the image, and then some form of upscaling tool that it can use to improve the image. And it's also interesting to think that, the latent is more like the information part, and the network is more like the kind of action or program part. But as far as like the neural network is concerned and information theory is concerned, information is just information, so it can optimize both at the same time. So results, just to give you an idea. So these are Coolsheik results I got from their website. So they're version 4.2 on the Kodak image suite that probably everybody knows here. So if we look at the gray dash line here, that's HEVC or HM on these images. And then it's a bit hard to see, but the gray full line here, that's VTM, which is VVC. So this would be state of the art. And then the orange line is Coolsheik 4.2. We can see that, it's close, very close to state of the art in like for high quality. And then if we go down, it's not as good, but it's still very competitive with HM and VTM. So HEVC and VVC. And I think that kind of breaks the myth that, this is like, not ready or a lot slower. I think and Coolsheik is just kind of one of the basic ones that I can explain to you. There are more complicated ones that can get, somewhere from 5 to 10%. I think some as high as 20% better than VTM. So, but this is, a simple approach that's easy to explain and fits into this like 101 overfitted codec tutorial. And you can see that's doing quite well. It's also surprising because as a field, this isn't really old. And it's already, very competitive with traditional codecs, which are a lot older and have benefit from a lot more experience and a lot more manpower behind them. So
I have a question.
Sure, go ahead.
So the if you go back to the previous slide with the network, which aspect, would it be the latent that would be the compressed output in this case, or
both are. So
What's the other thing?
the other thing are the weights of the network.
Oh, I see. Okay.
So basically, the payload is the latent, and then the weights of the network, and then there's a bit of metadata to say, the size of the layers and a little bit of information just to put everything together.
And the totality of those things would be the bit rate used.
The
Like,
totality is the bit stream, and then yeah, the size of that is the amount of rate used, right? So it's
oh,
the
okay.
and then what's interesting, like I said, is that it can actually know that. So as it optimizes itself, it compresses itself also.
Hmm.
So your back propagation is giving you, compression out of just optimizing the weights by the way that we've made the error function. So the results. And then another thing that was to me that's very interesting in these type of approaches is I kind of referred to them as living codecs. So the idea there is that because you have the weights, and like we just talked about, because you have the weights and you have the latent, if ever you get the source image again, or if you keep the source image, you can actually just recompress the image, or you can continue compressing the image. So you could think about it as like a living codec that just has all the pieces it needs to continue being compressed. Which, is something you can't really do in modern codecs where you tend to have to start from scratch. So the takeaway from my talk is, I think gradient descent is the encoder, or is the next encoder. Basically, we've shown that, in traditional codecs, you're going to use this kind of block-based approach, and you're going to end up with these like local optimizations. So you're going to optimize block by block and try to take the best decision. And what's interesting about overfitted codecs is that you've got the whole representation of the image before you, and then you can optimize the image entirely all over the entire image, right? So you can find global optimums, and it's not just this combination of local optimizations. You really have this thing where you can work over the entire image, and then your gradient descent finds the most important parts of the image to optimize, and it keeps building as it goes. I think that's interesting. Like I said, this is just a small introduction, short introduction to overfitted codecs. There's a lot more to it there, but I hope that gave you like a starter pack to keep going afterwards and continue on that journey if that interests you. So that's it for my talk.
Awesome.
I'm open to take questions if there are any.
I have another one. Thanks a lot. First off, but this is pretty cool. Definitely really neat to kind of see this in action and see it kind of, I want to say, dumbed down for us who aren't experts in the field. My question, I guess, is the network would have to be trained on per image, right? So like
Yep.
you couldn't take a trained network, and if you give it another image, it can do compression, like a similar compression on it. Okay.
No, exactly. So that would be more like an autoencoder.
Oh, I
So,
see. Yep.
so the idea here is really one video format per image. So you'd have this very specific ultra, you'd use machine learning to build a codec for specific to the image you're encoding. So I think that's
Yep.
the idea behind that.
Oh, okay. I guess a follow-up would be, what's the speed of these types of no, like doing this system here to get to whatever rate you want? Like, is it a second, or is it like
No,
a
this
couple
is
seconds?
this
Yeah.
is very slow, right?
Yeah.
Okay, so
Yeah.
just to give you an idea, when we went to click, I think they had to postpone part of the competition because some of the results weren't done, and they had started them like a few weeks earlier. So it is very slow. These require like when I'm talking about the most advanced approaches, they'll require like these very expensive GPUs, and they have 8 of them, and they make them run like 8 hours or 24 hours to encode just a single image. So
Okay.
one of the interesting things with Coolsheik is that the final approach I'm showing here is that it's actually quite fast. It requires somewhere between like 1,000 to 10,000 iterations because of the latent. So you can actually, it's usable. And if you go into the GitHub repo that they have for the project, they actually made a C decoder, because decoding is actually very fast, right? You just apply the neural network, so it's just linear operations. And that one I think is real time. So the decoder is real time. The encoder takes a bit of time, but then they show you, you know, depending on the amount of iterations you're willing to spend, how much compression you get. But definitely that is the frontier here, is that these are very complex network. These are big networks. And but just to give you an idea, I think it's almost like a 10,000 to 1 compared to like autoencoder training and things like that. So it's faster than different other solutions that are out there, but it's still very, very expensive. And that's definitely what they're working on, is trying to make it faster and I guess more practical also, because we haven't even talked about the whole product to like making a product out of this. But
Yeah. Sushmita, you had a question?
Hello, I hope you can hear me.
Yep.
I have a question. If thanks for the interesting presentation, first of all. I have a question if maybe this can be applied to just image patches, and if that could be a form of rate control.
Yeah, that can be applied to patches. I think I've seen versions that do like these like 64 by 64 and 256 by 256. But then you end up with like multiple models or multiple networks or MLPs per patch. But I think that was done, yeah, for patches.
I see. Thank you.
Sure, you're welcome.
We have a message from Lorenzo Catania about doing some research in INR and improving computational times. And he's inviting people to connect if they're interested.
Yeah,
Scott,
so
you have a-
INRs are like a whole field, right?
Oh,
One of
I
the
see.
application is image compression, but I think if you've seen these point clouds or 3D representations, I think INR are useful there. At least they were a few years ago, and I think they're being replaced by other things like Gaussian splatting. But there's definitely, so it came from another field, and I think the latent representation also came from another part of machine learning. So it's also interesting to see that you know, these different domains are kind of feeding into one another. So you see the researchers working on learn compression, taking things from point clouds and other fields.
Was there another question? I thought I saw something. Scott?
If you were to be picking up some of this data, like where it's trained on, would a lot of it be sRGB data or video codecs? Like, is it kind of basing it off of what you put in, or is it already kind of piggybacking off of pre-existing machine learning of YouTube or something along those lines?
So for the INRs, they're the Siren version, they have their own data, but it's actually like a mathematical optimal starting point that they've derived. But no, I don't think there's an actual, I think they just start with random data for the weights. I don't think there's a starting point, but yeah, that's definitely something that can be explored.
And if I were to throw like is this like in moving images exterior, like what I see from the references here? But if I were to do like a nightclub scene where there's a strobe light going, would that throw so many different variations into the mix that it would really be hard to pin down what the compression output would be?
So like right now for video, they're like, that's still work in progress. I think there is a version of Coolsheik for video, but I had talked with the auditors and they were saying that right now they're still having a hard time with like the temporal aspect of it, because just the amount of information you're processing is huge. So, but it would not be like one network per image or per frame. It would be like this. So imagine you would be able to say like, give me this video from this frame or this pixel from this frame. So it would actually be a whole network for the video or something like that, or for a GOP or something.
Thank you.
Ali?
Yeah, thanks, Luke. So the question I have is that in traditional codecs, as we know, there is the concept of graceful degradation, right? So if, for example, motion estimation, there is no match, you pay for it by having a bigger residual, right? Is there a concept like this in this scenario? Like if, for example, something happens on the receiver, would they end up with, instead of having that picture, the photography with something that is really weird or something that doesn't really get close to the original image?
Yeah, you're saying if the data would be like broken or something, or
Yes.
disrupted? Yeah, I don't think that that field is that mature yet. So I don't think they've figured that part out. So one thing that one way the data is split is you'll have the latent. So you could even imagine just coding the image directly inside the latent, having no network, and then having the network kind of build itself up and compress the latent. But there's nothing for resiliency, or at least not from what I've seen so far. I think this is more like proof of concept, and then the big issue right now, like I said, is computation. So they're trying to get this down by like another factor of 1,000, because like right now I think they're in like thousands of operation per pixel, or thousands of multiplication per pixels. So that's huge.
Okay, thanks.
Ahmed has said videos, there is a nerve model where you give it an index A and returns a frame, and then there's another variant, high nerve, where you give an index and returns a patch of the video.
Right, exactly. So that's another approach. Yep.
Well, any other questions? If not, then I want to thank everyone for coming out in the middle of the day. It's a great turnout, and I want to thank you, Luke, for finally allowing me to get you to come in and do a talk. I know you have a lot of topics that you're very passionate about, and you're super knowledgeable and the valued member of the community. So appreciate you taking some time and sharing it with us.
Sure. Thank you very much for having me.
Yep.
Thanks, Luke.
Yeah. All right. Thanks, everyone. Enjoy the rest of your day. Bye for now.
Bye-bye.
Thank you. Bye.